This is the 2-5 notes for Calculus 1. In the previous section, we talked about infinite limits. Specifically, if we took the limit of x goes to 0 of 1 over x squared, we learned that that is going to be equal to infinity. So 1 over a tiny number is essentially going to be a very large number. So the inverse scenario of that is what we call a limit at infinity. So what does that look like? We'll just take our 0 and change it to an infinity. So look at this guy. So what we want to do is we want to take our same function that we're dealing with, and we want to see the behavior as we increase without bound, essentially, to infinity or negative infinity. So if you look at the same exact table from the previous lesson, if I just started plugging larger and larger numbers of x into this function, 1 over x squared, what would I get in my result for the actual function itself? Well, it appears that I'm getting smaller and smaller numbers that all appear to be heading towards 0. So what that tells us is that the limit of each one of these limits at infinity is going to be 0. We can further see that by looking at the graph of 1 over x squared. And as these approach an x value of infinity or an x value of negative infinity, they are not crossing but going right up against the x-axis, which is the equation y equals 0, which is indeed our limit. It turns out that similar to our previous section where we had a vertical asymptote that was as a result of doing a infinite limit, we can actually generate a horizontal asymptote as a result of a limit at infinity. So for example, if you look at, let's say you know that the limit as x approaches infinity of a function is equal to some value. So in this case, if you look at our example here, the limit of x goes to infinity of our function 1 over x squared was equal to 0, which we would refer to as L in this problem, basically. So what does this say? It says, in this case, the line y equals L would be a horizontal asymptote. So if you look at this, applying the definition, since the limit of x goes to infinity of 1 over x squared is equal to 0, then we would say that the horizontal asymptote is equal to y equals 0 because that is our value of L. Now this is different from when we talked about vertical asymptotes and infinite limits, because we would say that the vertical asymptote was all about what x was approaching at the time. So now the horizontal asymptote of a limit at infinity is actually going to be the resulting limit value for our actual function. Okay, so we'll put this all together in a minute, but let's take a peek at a very simple generalization about limits at infinity that always seem to fit. Now, it says if you take the limit of x goes to positive or negative infinity of some constant over x to the r, that will always be 0. So what's an example? How about the problem we just did? We took the limit of 1 over x squared, which is a constant, over x to some value. What's another one? 2 over x cubed. That would be another. So that what it's saying is the limit of x approaches infinity of any number values that fit this mold will be 0 no matter what. And that makes sense because if you plug infinity into the denominator, you're getting 1 over an infinitesimal value, which means you're going to get a very, very tiny value new 0. That's going to be the key. So let's look at a quick example of something that we wouldn't have been able to do before, but now we can with this new rule. So let's say we wanted to find the limit of x goes to infinity of 3 plus 1 over x. So limit laws allow us to write this down into two separate values because of this plus sign. So we can break this into two different values. The limit of x goes to a negative infinity of 3, and the limit of x goes to negative infinity of 1 over x. Well, we know that the limit of a constant is always going to be that constant no matter what is going on right here. Doesn't matter. Limit of a constant is a constant. But you now learned, based on this right here, that the limit of x goes to infinity or negative infinity of any constant over x to a power, in this case r would be 1, is always going to be equal to 0. Therefore, the limit of this function is going to be 3. So just to be clear on that, I'm going to rewrite it over here. So the limit of x goes to negative infinity is of 3 plus 1 over x. Our function is equal to 3. So if we go down here, if we sort of apply the definition that you learned right here, then we now know that if we have the limit of x goes to some infinite value of a function, and it's equal to L, then y equals L will be the horizontal asymptote. So if we go by that logic, then what is L in this problem? It is 3, which means y equals 3 is going to be our horizontal asymptote. So why don't we just look at the graph? So the graph of this function here, right here, is down here, right? And let's look what it looks like. Well, according to this, our horizontal asymptote is y equals 3. So look at this. Hey, we have a horizontal asymptote of y equals 3. So it actually works real well. And if we wanted to find the behavior of this graph as x approaches negative infinity, then that would be going that way on the graph. So we would be like, all right, well, we got to go this way. So what value of y, what height does this seem to be approaching but never cross? That appears to be 3, which is exactly the result of what we got in this scenario. Okay, we can now take what you've just learned in order to apply it to polynomials and rational functions. Polynomial, rational functions. So let's talk about polynomials first. Well, with polynomials, limits can be very easy because it's all about the leading term. So if you remember from pre-calculus, you talked about end behavior whenever you dealt with polynomial functions. And end behavior was always based on whatever the highest degree term was. So basically, what we do in a polynomial, believe it or not, is we just take the limit of x goes to infinity of the leading term, and that's it. Now, what does that look like? It'll be a little weird, so we are going to take our infinity and plug it in here and get 2 times infinity to the 4th. Well, if we take any value to the 4th power, it becomes positive, so we're going to get 2 times infinity. And 2 times any big number is just going to be a big number. So therefore, the limit of x goes to infinity of this function is indeed just positive infinity. It's kind of weird. It's actually called an infinite limit at infinity. I know that sounds kind of weird, but that is what you get for this scenario. Similar problem. What about the limit of x goes to negative infinity of this function? Well, you have to be careful. If you look at this guy right here, the leading coefficient has now moved. So we're now doing the limit of x goes to negative infinity of negative 3x to the 5th. Again, what do we need to do? We need to plug this into our function. And what does that look like? That's going to be negative 3 times negative infinity to the 5th. Negative infinity to the 5th. Anything to the 5th, basically, or any negative to the 5th stays negative. This is just basic math rules. Applies to infinity as well. So we're going to get negative 3 times negative infinity, which is going to give us positive infinity. Remember, the 3 is of no consequence because 3 infinities is still just infinity. It's the key that negative times a negative gets us a positive, so we end up with infinity for this problem as well. Okay, it's a little bit different take when it comes to rational functions for this guy, rational functions. Okay, whenever you have a rational function, the goal is always going to be to manipulate the problem so we can actually use our rule right here in order to determine the limit. So we're trying to manufacture constants over x to the power. So how do we do that? Well, it's clearly written here. We want to divide each term of both the numerator and denominator by the largest power of x in the denominator. Okay, so what does that look like? Well, look at our first problem. So we got this rational function, which is basically just a quotient of polynomials. We clearly see it's a limit at infinity, so that's our signal to use this type of strategy. So what is the highest power in the denominator? It's x to the 4th. It happens to be the highest power in the numerator too, but that doesn't matter for what we're doing. We just want it to be the highest power in the denominator. So we need to divide every term of these numerator and denominator by x to the 4th. So what does that look like? We get 3x to the 4th over x to the 4th plus x x squared over x to the fourth minus 6x over x to the fourth all over negative 5x to the fourth over x to the fourth plus 7 over x to the fourth. All right. So once we get to that point, we can then separate it into an entirely different value. What do I mean by that? So basically what we're doing is we're first finding the limit of x goes to infinity of our first value, 3x to the fourth over x to the fourth. Well, let's simplify this even more and get the following. So this is going to be 3. This is going to be 1 over x squared. This is going to be 6 over x cubed. Just simplifying here. This is going to be negative 5, and this is going to be still 7 over x to the fourth. If we now take the limit of x goes to infinity of all 5 of these values, so this, and this, what do we get if they were individual values? Well, the limit of a constant 3 is 3. The limit of 1 over x squared, well, guess what? We're back to here again. Constant over x to any power, the limit is always going to be 0. Well, what's the limit of negative 6x over x cubed? It's 0. What's the limit of negative 5? That's a constant. What's the limit of 7 over x to the 4? It's 0. So what do we get? We get negative 3/5 as our limit for this problem. So a little bit different concept, but very easy to come up with. Okay, I will return in a second to the meaning of this in horizontal asymptotes because in pre-calculus you actually learned about 3 different types of horizontal asymptote scenarios that you could get, and this is one of them. I'll get to that in a second. Let's do the limits first. So 4. So same thing here. What are we looking for? Highest degree in the denominator, which is x to the fourth. So we need to divide. Well, let's divide, but let's do it a little quicker. So bring down the limit here. Negative infinity. What's x squared over x to the fourth? That's 1 over x squared. What's 5x over x to the fourth? 5 over x cubed. What's 9 over x to the fourth? Well, nothing simplifies, so you get that. What's 2x to the fourth over x to the fourth? It's 2. And what's 3x cubed over x to the fourth? It's 3 over x. So now what can we do? We can then apply this limit individually to each value. All 3 of these on the top are all constant over x to the r. So we're going to get 0 minus 0 minus 0. Then we have a constant sitting here, and then we have another 0. So what do we get? We get 0 over 2, which is 0. So the limit in this problem is clearly 0. All right, last scenario, 5. So what's the highest degree of the denominator? It's x cubed. Okay, so be careful. Don't take the highest degree because it's x to the fifth in the numerator. We want only in the denominator. So what do we get? We get the limit as x approaches negative infinity. Well, if we divide x to the fifth by x cubed, we get x squared. Then we get 4 over x if we divide by x cubed. Here we get 1 over x cubed, and here we get 5. Okay, this is when things get a little tricky. So I'm just going to skip this one, x squared, for a second and do the ones we know. What's 4 over x? It's 0. What's 1 over x cubed? It's 0. What's the constant? It's negative 5. But what is happening here? So if I want to know the limit of x goes to negative infinity of x squared, well, it's similar to this setup over here, right? Similar to this, where I need to just figure out the signage of this. So if I plug negative infinity into x squared, it's basically negative infinity squared, which is a positive infinity. So that goes in there, which is going to be negative infinity over negative 5. But looky here, just like if I multiplied infinity by a negative, I'd get a negative infinity. If I divide, I also get a negative. So I get negative infinity as my result for my problem. So just note, we do have 3 very different answers. We have a number answer here, we have 0, and we have an infinite answer. Well, these are the 3 scenarios that you could run into whenever you're dealing with rational functions and limits at infinity. Okay, so let's take a peek at how this results in end behavior and the asymptotes of rational functions. So if you look at just our setup for this, basically the summary of what you learned in pre-calculus is listed down here. So I'll talk about that a little bit as we go through it, but I am going to start at B because B was our first problem. What does it say? Well, first of all, It defines a rational function as p over q, or just polynomial over polynomial. And it says that the highest degree of the numerator is m, and the highest degree of the denominator is n. So that for letter B, our first example is when the two degrees are the same. So what does that mean? If you go to our problem over here, look at the degrees of our highest degree of the numerator and denominator. What is the relationship? They are the same. They're both 4. So that means that this is the rule here that we need to use. So what happens in that case? What we do is we take the leading terms of those coefficients and put them in a fraction. That is always going to be A, the limit, and B, the horizontal asymptote of the function. So let's look. So look at our leading coefficients for our values, 3 and -5. So according to this, 3 over -5 is going to be the limit. Yeah, it is over there, -3 over 5. And it's also going to be the horizontal asymptote. Well, we knew that already. Why? Because the answer limit of this is always going to be the asymptote. So that means we can go down here and say for number 3, our asymptote is y equals -3/5, which is our result over here. So what's another example? Well, what if we're looking at a scenario where m is less than n? So let's get rid of this one and concentrate on that one. So if the numerator has a lower degree than the denominator, so let's look at that. X squared and x to the 4th. So the degree is 2 and the degree is 4, clearly numerator less than denominator. According to this rule, the limit will always be 0, and the horizontal asymptote will be y equals 0. So let's see what happened. Look at this. The limit will always be 0, and therefore this will be y equals 0 will be the horizontal asymptote. So down here, y equals 0 will be that. And this can all be checked using graphs as well. The last one, if you look at number 5, this is obviously the remaining example, which is what if the degree of the numerator is bigger than the denominator? So let's look at that. So x to the 5th and x to the 3rd. So that is exactly what happened. According to this scenario, your limit will always be infinity or -infinity, and f will have no horizontal asymptote. All right? So let's look at our answer. Indeed, we do get -infinity as a limit, but it makes sense. How can we write y equals -infinity as an asymptote? An asymptote is a physical line. It can't be an hypothetical large value, which means this is our clue in this problem that our asymptote does not exist in terms of our problem. But there is one small part to this which I don't really show in this class, but you might have learned it in pre-calc. When you do an actual asymptote for this guy right there, that means that there's going to be a slant asymptote instead. So just realize we will get a slant asymptote if we try this as a result of what we're actually going to be doing for these unique scenarios. And just to be clear, you don't have to know anything about a slant asymptote. You just have to be clear on these specific 3 scenarios and how they apply to rational functions and limits at infinity.